Hi, my name is ADLINA NORHAYANI binti RASHID. So I'll be presenting about the background of this project, and also I will explain about the process of the separation, basically on how the flash separator works. Okay, so first, this project is about designing a flash separator to separate a toluene and benzene mixture. The project contains detailed information on how the process of separation works, the process conditions, assumption, and also the calculation for the separation of the mixture. So why it is important to separate the mixture? As you can see, our team get the mixture of toluene and benzene. So crude benzol is a significant byproduct of coke oven gas. By extracting and processing crude benzol, important compounds such as benzene, toluene, xylene, and solvent naphtha are generated. Benzo compounds are usually utilized in pharmaceutical, organic chemical industries, paints, and other applications. So our goal for this project is to analyze the process and the typical condition for separating the mixture of toluene and benzene. And the second goal is to determine the moles of liquid, moles of vapor, liquid phase mole fraction, and vapor phase mole fraction of the mixture of toluene and benzene. Okay, so let's take a look at the process on how the flash separator works. A liquid stream containing benzene and toluene partially vaporized in a flash drum at a pressure of 68.65 kPa and temperature of 80 degrees Celsius. This results in two phases, a vapor phase enriched in the more volatile components and a liquid phase enriched in the less volatile components. So first, the fluid is pressurized and heated and is then passed through a throttling valve or nozzle into the flash drum. So, at the flash drum, because of the large drop in pressure, part of the fluid vaporizes. The vapor is taken off overhead, while the liquid drains to the bottom of the drum where it is withdrawn. And lastly, the system is called flash distillation because the vaporization is extremely rapid after the fluid enters the drum. Because of the intimate contact between liquid and vapor, the system in the flash chamber is very close to an equilibrium stage. So next, for the next slide, we will take a look on the process unit. So this is the process unit for our flash separator. As you can see, the toluene and benzene enters into the flash separator and is then separated into vapor mixture and also the liquid mixture. In the vapor mixture, the more volatile components will be in a higher number of molar fraction, and in the liquid mixture, the less volatile components will have a higher number of molar fraction.
For the assumption, firstly, we assume that the mixture is an ideal solution in which the enthalpy is equal to 0. Next, we assume for the inlet temperature, which is 80 degrees Celsius, since the boiling point of toluene is 110.6 degrees Celsius, while the boiling point of benzene is 80 degrees Celsius, so we just assume the temperature in between of that boiling point temperature. For the pressure, we choose 68.65 kilopascal. This is because the assumption must be in the range of the pressure due and pressure bubble of the mixture, where we can get from the calculation. The calculation shows P due is 56.2109 kilopascal and P bubble is 70.110 kilopascal. So the pressure that we assume is reasonable. Lastly, mole fraction is in equivalent mixture. Equivalent mixture is chosen to increase the amount of toluene produced at the bottom of the flash distillation column and the amount of benzene produced at the top of distillation column. In addition, the assumption that we chosen is in optimized condition where we can achieve high purity, high production and less energy consumption.
Okay, next for the calculation part, in order to find mole fraction of toluene and benzene, we need to assume that the reaction mixture is an ideal solution. By using Ross's law, YIP equals to XIP set, where Y is mole fraction of vapor, X mole fraction of liquid. Next, to find the P set, we need to use the data from table B2. We need to find all the parameters for entire equation, which is A, B, C. Next, by using Entore equations, which is ln P set equal A minus B T plus C. For P set toluene, we can get 38.8 8932 kPa. For benzene, P set equal 101.3287 kPa. To find P bubble, we can use equation from the textbook, page 455, equation 30.16, and we can get 70.110995 kPa. To find PD, we also use this equation from books, and we can get PD equal 56.2109 kPa. Next, from Rock's law equation, we have K1 equal Y1 over X1 equal P set over P. Then for K toluene, P set over P, we can get 0.5665, and for K benzene, we can get 1.476.
As we finish the calculations for the K values of each components, next we calculate the vapor mole. So for calculation of vapor mole, we're using the equations 13.106 in 8th edition textbook, which shown in the figure. And then from these calculations, we can calculate by using two methods, which are trial and error and iterations. Before we proceed to calculations part, we have to understand what is mole of vapor and liquid. Mole of vapor is like the mixtures of two or three components of same physical properties which are in vapor, and then they mix together, they sum together to get the mole vapor. And same goes as mole of liquids. So in these solutions, we calculate the mole of vapor by using trial and error methods in MATLAB. So in the big figure that shows the MATLAB programming, and then after the results come out, it said that the value of the vapor fractions is 0.103 mole. After we finish calculate the mole of vapor, so we can able to get the mole of liquid. Since sum of mole of liquid and vapor was 1, so we minus it, 1 minus it, and we become 0.897. Then we sub into the equations 13.105 to get the vapor mole fraction of each components, which are toluene and benzene. After finish calculate the vapor mole fractions of each components, we able to calculate the liquid fractions by using the formula mole of vapor of each components over the K value for each components, and we can get toluene of the liquid fraction was 0.523 while benzene was 0.477. After finish calculate the mole fraction, the last questions mentioned that we have to calculate the mole of each species. So we have to using mass balance calculations, and then mass balance was total mass in equals to total mass out. Before we calculate the mole balance equations, first we have to do the assumptions. We assume that the total inputs are 100 mole of toluene and the benzenes. So as we calculate the mole fractions of liquids and vapor for each components, we can calculate overall equations. 100 equals to N2 plus N3, and then we using toluene balance that 0.5 times with 100 equals to mole fractions of vapor times with the output for the vapor mole, and then 0.523 times with which are the mole fractions of the liquid times with the mole of the liquid. So by using substitution methods, we able to get N2 is 10.102, and then N3 was 89.868 mole.